All right, welcome back to Physics 221, Chapter 16, Traveling Waves. So we've pretty much completed the section, the important sections on traveling waves. Now we're just going to do some seemingly random topics which are really important about waves. So first, in the 1860s, there was a guy named Maxwell from England. And at the time, lots of people had done experiments on electricity and magnetism. So there are all these results, but no one had written a mathematical theory. And you always want to have a mathematical theory because then you can use that to predict new things. So Maxwell decided to go off and write the mathematical theory of electricity and magnetism. And he did that, and when he did it, he had 20 equations that described everything that they knew about classical electricity and magnetism. And then over the next 20 years, other people looked at those 20 equations, and thankfully they kind of whittled them down to 4. So these are the 4 Maxwell's equations, which again, they explained everything there is to know about classical electricity and magnetism. Now, I don't know what's the deal with this computer here, but this rectangle is supposed to be a circle, all right? The people who took Physics 220 last semester are well acquainted. We basically spent almost an entire semester learning about these 4 equations. All right, now these equations are in terms of vector fields. This is the electric field, and this is the magnetic field. They're not in terms of particles, which is kind of interesting. Maxwell's equations predict that when you disturb an electric or magnetic field, the disturbance travels, it's a wave, basically. The disturbance is a wave, and the wave travels at 3 times 10 to the 8th meters per second, which is the speed of light. And people knew it back then. So basically, Maxwell predicted the existence of what we call electromagnetic waves, which is a fancy way of saying light. Now, F equals ma. V equals F lambda. But here, the velocity of these electromagnetic waves, or light waves, is the speed of light. And we always use lowercase c for the speed of light. All right, so Maxwell's equations say that these electromagnetic waves, or light waves, they have to have one speed, the speed of light. But, you know, speed of light equals the frequency times the wavelength. So these two can be anything as long as their product equals the speed of light. All right. Now, okay, so that was his prediction, right? That was just purely prediction. He was a theoretical physicist, didn't do any experiments. So the first evidence for his theory, 20 years. It took 20 years before there was, evidence that this prediction about the speed of light was correct. Unfortunately, Maxwell had died already. He died at 47, so he never got to see that verified. Okay, now let's go back. So this is constant, right? Speed of light is constant. But again, the wavelength and the frequency can be anything. So this is what we've learned. So this is called the electromagnetic spectrum, or the light spectrum. It basically shows you the different types of light that we know about. So gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio. Those are all types of light. They all act like waves, and they all travel at the speed of light. It's kind of interesting. So you look at all of this, and this is visible, just this little tiny region here. So, when you think of the entire light spectrum, how much of that is made up of visible light? Not very much, right? Okay, so let's look at the size of the wavelength. So you see here that gamma rays, the wavelength 10 to the minus 12 meters. That's pretty small. And then you look at radio waves, they can be 100,000, a million meters long. So there's this incredible range of sizes. Yeah, here, this is pretty good. So this is the size of the wavelength. Hydrogen atom, protein, bacterium, animal cell, pinhead, baseball, football field, and longer. Here's the frequency, 10 to the 20, 10 to the 16, 10 to the 12, 10 to the 8th, 10 to the 6th, 10 to the 4th, and so on. And there's different energies, 10 to the 6th, 10 to the 4th, 10 squared, 1, blah, 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 10 to the minus 8. So basically, radio waves have very, very little energy. And that shouldn't surprise anybody because, I mean, how many radio waves are going through this room right now or where you are? A lot, right? And you can prove that just by turning on your radio. And we don't seem to be harmed by those radio waves. On the other hand, they use gamma rays in hospitals to kill cancer cells because they have a lot of energy. All right. Now, something else. Okay, so years ago, astronomers, all they had were visible light telescopes. And so all they were seeing, I mean, here's this entire spectrum of light. All they were seeing was this little tiny region. And then people figured out how to make telescopes and satellites that covered almost the entire region. So let me show you that. Okay, here's what I'm talking about. So here's a constellation, visible light. So this is what you see in the night sky, right? See this? Okay. Now, this is what you see with ultraviolet light. So think about it. You're used to seeing this, Orion, right? You're used to seeing that, and then all of a sudden somebody shows you that in the ultraviolet. You say, whoa, what's going on? You got to explain all that. And then somebody shows you this in the infrared, and there's even more going on. So, this astronomy has undergone a huge revolution because now, they have radio telescopes, microwave satellites, infrared, UV, X-ray, gamma. So they've almost covered the entire spectrum. So they're just learning all sorts of really cool new things. All right, now it is time for a DVD. So we shall watch.